a week passed since my last talk, so I should recall some notations and introduce some new notations. So from now on, we'll be interested in an algebraic projective algebraic variety Y, non-degenerate, lying in this projective space, and we will denote by X its second Veronese embedding. So the image lies here in projective space of dimension nu, whereas nu is equal to this number, where E2 is the number of quadratic equations, linearly independent quadratic equations of Y. So
the second Veronese of Y?
Sorry. When we embed Y, the image can be degenerate, and it is contained in a hyperplane if and only if Y is contained in a quadric. And so we get this embedding. And the invariants that we introduce are as follows. First, K2 of Y is defined as follows. We consider this ascending nested chain of embeddings, where this is a secant variety, for X. The secant variety is 2, and so on. And finally, at a certain step, we first get the ambient projective space. So at the step K2, we get P nu. And this smallest number K2 is is denoted by K2, and in the according to the definition I gave last time, we see that K2 plus 1 is the order of variety X. There I didn't consider quadratic embeddings. I defined this for any projective variety. So this is our first invariant, or rather the second, because the first invariant is E2, then K2, and then we get a sequence of secant deficiencies of this second Veronese embedding. They are denoted by delta, delta K. And I recall that for any variety X, not necessarily a quadratic embedding of other variety, we define this secant deficiency in the following way. We considered as K as a join like this, and we take and we define delta K as follows. So this is the expected or maximal dimension of this secant variety, and this is how this dimension drops. And there was another interpretation of delta, which is as follows. We take a general point of this variety, and we consider its entry locus. So we denoted it by sigma U, K, and it's the locus of all points X, such that this point U is contained in the line passing through X and some point V, or lying here in the preceding secant variety. And so then delta sub k is the dimension of this entry locus of the point u. And now we'll study these invariants for arbitrary varieties y, but before, and their properties. But before passing to this detailed study, I would like to explain informally why quadratic embedding are better than just to consider any variety. What is so special about them? And the answer is as follows. Last time I studied in detail a very special example, which is of variety, also of quadratic embedding. This is the Veronese variety itself. And in this case, I just recall, so if you wish, you can say that this is x for y equal to linear space. And in this case, we saw that delta k is equal to k for all k between 0 or 1 and n, and we describe the entry locus. We take any point u here, then this means that u is contained in the linear span of the 0 the k for some so the 0 the k the points in x in z, and then what is the entry locus of this point u? We saw that it's described very easily in the following form. This is the Veronese image of the linear space spanned by these points. So this is a linear space of dimension k, and this is just its embedding. And you see immediately that the dimension of the space is k, and this means that delta k is equal to k. So we have a very nice geometric description. And if we consider the sequence of these secant varieties for this, and this, I recall that this is the variety corresponding to symmetric square matrices. We get the following ascending nested chain of varieties. And nu here is, of course, the one we saw before. This corresponds to matrices of rank at most 1, 2, 3, and so on. And I recall that we have n plus 1 variables, and so this is the last. This is the space of all matrices. So this is filtration according to the rank of the matrix. And here we have the dimensions. This has dimension n. This has dimension 2n. This has dimension 3n minus 1, and so on. And finally, the preceding has dimension this number nu, so has dimension nu minus 1. So this is a hypersurface whose equation is just given by the determinant of this symmetric matrix. We know all this very well, but I recall that if we have an arbitrary variety of dimension n, say x, then the expected dimension of secant variety is the following. It's k plus 1 n plus 1 minus 1, I think. So for example, for k equal to 1, we get 2n plus 1. This is the largest possible dimension. And here we have drops because of these deficiencies. And so this chain of varieties grows rather slowly, much slower than one could expect. And now consider this, our example x. X is contained in Z. because since y is contained here, x is contained in z. And we consider, just right below this, we write this sequence for this chain of varieties for x. And of course we have inclusions. Here we have this inclusion, here we have this inclusions, and so on, because y is contained in this linear space. And therefore, this gives an upper bound, if you wish, for the dimension of this variety. So we know that in this chain the dimensions grow rather slowly, and this shows. Suppose that here we have all deficiencies equal to 0, which is often the case for arbitrary varieties. Then this means that in this chain the dimensions grow very rapidly with this rate of growth. And if you have something growing rapidly dominated by something growing slowly, you must have at certain point stabilization. And so this means that you should have some deficiencies under very mild conditions. You need, if you know that this rate of growth of this sequence of the dimensions is bounded by something, then it cannot grow always with the maximal rate. It should somehow grow slowly, and this means that you should have deficiencies. Furthermore, what does it mean that y has quadratic equations? That means that x is degenerate. And that means that actually for this secant variety is not only contained here, but also contained in some linear subspace of codimension E2. And this gives a further bound on the dimension. So this hints that if we have many quadratic equations, then this should mean that we should have more non-zero deficiencies, and they should be larger. And so this means that because this second Veronese variety is so exceptional, we should consider this invariance for second Veronese embeddings of arbitrary varieties, and we can hope to have some non-trivial invariance. I should only point out here that this is not Veronese variety like this is not the only variety with this property. As we already saw, we can take arbitrary variety, for example, of square matrices. And then if we have any variety contained here, then we also have some bounds for its secant deficiency. If we have here small codimensions, that means that it should have deficiencies also. Still more, we should have even more deficiencies if, for example, we have a subvariety of not so big codimension in the Grassmann variety of lines, because here the deficiency is even equal to 4, because G1R contains a lot of Grassmannians of lines in P3, and Grassmannian of line in P3 is a 4-dimensional quadric. And therefore this quadric should be contained in the entry locus. And so this means that deficiency of the Grassmann variety of lines is equal to 4. And so one can perform similar study for subvarieties of these varieties and many other varieties. But Veronese is exceptional because what I am going to tell you, it applies to any variety y, because any variety, projective variety, is contained in a linear space. And therefore this is the most general theory, and if someone needs to study, for example, subvarieties of Grassmannian, which have very deep geometric meaning often, then one can proceed similarly. Okay, so this gives an informal explanation of what I'm going to tell you, and now we can start proving theorems. So the first the first problem that we faced with studying arbitrary varieties is that sometimes there need not be secant varieties at all. That's already the first secant variety is the ambient space. So this sequence stops very quickly. For example, this is always so if we have varieties of small codimension. So if X is a variety of small, Y is a variety of small codimension, for example, Y is smooth, and non-degenerate, and for example n is not very big, for example something like that, then from this it follows that the first secant variety is already equal to Pn. For example, if you have a space curve, then the first secant variety is equal to Pn, and so K1, here K1 for any y we can denote by K1 the first secant variety, which is equal to the ambient space. So here K2, because we consider it for the second Veronese embedding. And so K1 can be small, and this is inconvenient, because then this invariant is not interesting. So we'll see now that this cannot happen for quadratic embeddings. So the first, if you wish, lemma. Suppose that Sk of x in this notation is contained in the preceding secant variety of z, where z is, I recall that z is the Veronese embedding of the ambient linear space. That means that some point of the ambient linear space, general point here, it has rank k with respect to the variety x, or k plus 1 depending on the notation, but smaller rank with respect to this Veronese variety. And then I say that in this case k is very large. Not very large, but large enough. So this cannot happen, and in this case we have this equality. So unless the secant variety of z is equal already to the ambient space, which is the last step, we cannot have this inclusion. But of course, if it is equal to the ambient space, then this inclusion is obvious. Okay, so how to prove this? It's very easy. We should take, suppose that U is contained in the linear space, in the linear span of k points x. And these k points are the images under the Veronese embedding of points y before the Veronese map. Then we can consider this point u, but it's contained here, and we saw the interpretation of the entry loci for this point. So this means, from our condition it follows that we have the following inequality. because this point is contained here, therefore the entry locus, the inverse image under the Veronese map of this entry locus is a linear space of smaller dimension. But what does that mean? That if we have arbitrary k plus 1 points, general points of x, y, these are is a general collection of points, then they are not linearly independent. They are not in general position. But this means that that y is degenerate. It's contained in a linear space of smaller dimension. And our assumption was that it's non-degenerate. And this contradiction shows that this cannot happen. And from this, the following theorem is a consequence of this. We have immediately an inequality, which means that K2 of an arbitrary variety y in Pn cannot be smaller than the same similar number for the Veronese. For the Veronese, I recall that here we stopped precisely at this point, so K2 of, this means that K2 of Pn is equal to n. So why is this so? This is an immediate consequence of this lemma. We can write. We have so. This, and this is equal to the dimension of the ambient space. And so this is equal this is contained and in Sn of Z, because this is equal to the ambient space. All matrices have rank at most n plus 1. And so this inequality then follows immediately from this, because here we have that if K2, Sk2 is contained in Sn. So, suppose that K2 is smaller than n. So this is contained, of course, in Sk2. And Sk2 plus 1 is equal also to this space, because it stabilizes. But then it's contained here, and if K2 is smaller than n, this contradicts this lemma. And so we arrive at a contradiction. So n is the smallest possible value of this invariant K2, which means that we cannot arrive at a situation which we saw is often the case for varieties of small codimensions before Veronese embedding. So after Veronese embedding, we always have a sufficiently long chain of these secant varieties. So this is the first result. The second unusual result is as follows. we would like to compare the invariance delta for our variety y and its general hyperplane section y prime. Here it's a general hyperplane. It's often useful to compare this invariance, and of course in the case of arbitrary varieties, if we do this not for x, not for the second Veronese embedding, but just for any variety, usually these second deficiencies drop. For example, even if we take Veronese surface, for which we already know that delta 1 is equal to 1. If we take a general hyperplane section, what we get? We get a rational normal quartic. So if this is y, then y prime is a rational normal quartic, which means that it's the fourth Veronese image of projective line in P4. I recall that this is a surface of degree 4 and this is a hyperplane section, and of course for such a curve delta 1 is equal to 0. Because for any curve, as I explained already, except for plane curves, for any non-plane curve, the second variety has dimension 3. This is an easy exercise. So we cannot compare, we don't know how these invariants are related, delta k of y and delta k of y prime, except that of course for y prime they are smaller. But the situation for Veronese embedding is different. So we can say that delta does not change under taking general hyperplane section in this range. So proposition. In this notation we denote of course x prime by x prime the Veronese image of y prime, and then we show that we have this equality for k in this range. This means that we can simplify our task by cutting several times our variety by a linear space. Why is this? Again, it's very easy, easily follows from the descriptions of entry losses for the Veronese variety. So we take some points, k plus 1 points in this variety x prime, and we take some point u prime contained in the linear space, and we should study the entry locus here. We are interested in its dimension, and this is of course contained here. And we know that the dimension of this is delta k of x, by definition, in the general case. But we know, of course, that this is contained also here, where z prime is, of course, this linear span z prime is the Veronese image of this hyperplane, and we consider this section by a hyperplane, and the image of this hyperplane under the Veronese map is denoted by this. But we know what is this. If we consider everything in y prime in particular, we denote by this the inverse Veronese image under the Veronese map, the inverse image under the Veronese map of this variety. Then we can write it like this in the obvious notation. And it's contained here. And this we know what is this. We know that this is Pn-1, where this is our hyperplane. So this is the inclusions that we get for our hyperplane. And we know that because k is in this range, we see that this is contained here. Because this is contained in some linear space even of dimension k, certainly in some hyperplane. But then this means that they are equal, because this is a general point. Since the entry locus for y is contained in this hyperplane, then each point of this entry locus is also the point of entry locus for the hyperplane section. And that means that they are equal because there is this inclusion, which is obvious. In the other direction, it follows that from the fact that for a general point u here, it's contained in our hyperplane. And so that's the proof. Now we are interested in the behavior of this sequence of secant defects, and they have interesting properties. Some properties that is valid in general I mentioned in a lecture, maybe last lecture. So there I proved that for arbitrary variety y, the secant defects are monotonous. So we have and this is a very easy result, because if we have some point u in Sk of y, which is contained in a line joining some point of y and some point v in is k-1 of the preceding secant variety, and we have some entry locus here, then obviously it's contained in the entry locus of u. So if you have some k points here, then you always u is contained in the linear span of these k points and y. So this means that we have this inclusion, and therefore we always have inequalities like this. But these inequalities for arbitrary varieties needn't be strict at all. You can have a lot of equalities. For example, and this is a nice exercise, consider a scroll, a ruled surface. Any ruled surface, rational normal scroll, for example. So let S be a surface. You know that these curves are obtained by joining the corresponding points of rational normal curves by linear subspaces. So this is a fiber bundle over P1 over some rational curve which is the same as P1, and the fibers are also P1. But this can be contained in a linear space of big dimension. And then, for example, if you take two lines, two fibers, you have a lot of fibers. I denote them by F. And if you consider, for example, two fibers, F1 and F2, they span, these are two lines, and then span a P3. And if you take any point here in this P3, maybe this is not good, V, then the entry locus contains 2 points here. And if you consider more lines, you get more points. And finally, you see that although delta 1 is always equal to 0, starting from delta 2, you can get entry loci making up these fibers. And when you increase K, your entry locus contains more and more fibers. So it's reducible. But delta K is always equal to 1 until the last step when you get the ambient space. And so this delta need not be strictly increasing. But of course, the first several delta may be equal to 0. So I introduce the last invariant that we'll need. It's called L2. And suppose that for our variety X, which is the second Veronese image, we have the following. The first several deficiencies are equal to 0 until L2. But the next is not equal to 0 already. And because of monotonicity, all others, all subsequent are not equal to 0 either. So this is the last number of deficiency, which is trivial. And now we are able to prove the following theorem, important theorem. Consider an arbitrary second Veronese embedding, or arbitrary Y. Then suppose that we take some number between K, between L2 and N. Then we have the following strict inequality. So the function delta K is strictly monotonous. On this interval from L2 to N. And before, of course, if we write it like this, so L2, this is 0, it's equal to 0 before, by definition, and after that it increases strictly. Why is this? And how to prove this? So, let V, again we write the same thing, take a point U which lies on V, and X is of course in X. We write this, and then these are all general points, and we already proved that V is not contained in the preceding second variety of the Veronese. This we already proved. And similarly, U is not contained in Sk, because it's from K plus first second variety. And we have, in the obvious notation, we have these inclusions, similar to the ones I already wrote. And this is V2 of Pk. We already saw this. And similarly, we can write for sigma U and this is V2 of Pk plus 1. And we have sigma lies in the intersection, of course, and sigma V for Z. It's better to consider the inverse images, as we already did last time, and then I replace X here by Y. So I consider the inverse images under V2. And then we get that sigma Vy is contained in sigma Uy, and this becomes Pk. Yes. Sorry. No. I mistried to. So this is true, of course, but it's also contained in sigma, the inverse image of this, and this is Pk. The inverse image of this is Pk. This is sigma Zv, the inverse image of sigma Zv in the linear space. So we see that we have such an inclusion. What is the bad case for us? The bad case that we should exclude is that we have this equality. We want to prove that we have strict inequality. What does it mean? How can it happen? This means that sigma U is composed of the components of this. Because if this linear space cut properly our entry locus here, then we cannot have equality. So these components, and they do not change when we vary the point of the entry locus. Now we should exclude this case. Suppose that this is not so. Suppose that when we vary the point x prime in this entry locus, the corresponding sigma V prime, and therefore the inverse image sigma Y of V prime are stable, at least locally, which that means that they do not change. We get the same components. Then consider the family Pk V prime. I already wrote what it is. It's the inverse image under the Veronese of sigma Z V prime. I recall that this is always the linear space of this dimension. We consider this family for varying point. And then this family is also stable, because If it were not stable, then we take two members of this family and their intersection would be a linear space of smaller dimension. It will be, of course, a linear space, Pi, and of course, then, if it were not stable, I would be less than K. But this would mean that, contrary to our assumption, we have an inclusion here, not here, but in Y, in I. And this, we suppose, this is not the case, because our point was contained here, but not in the preceding secant variety. And so we get a family of stable linear spaces. And I draw the corresponding picture. So our point U is contained in some x1 and v1. But it's also contained in x2 and v2. And this is the same pk. So now we consider the intersection point of these two lines, x1, x2, and v1, v2. Not a very good drawing, it should be a line. So U is here. And we call this W. Now look, this W this W is contained in a secant line, x1, x2. This is a secant line of x. So this means that the entry locus is a conic. So a line in before the Veronese map. And this means that the corresponding points y1 and y2 are contained in the same pk. And therefore, U is contained in V2 of this pk, because all the points are contained there. And we get a contradiction, because this lies in here. And we assumed that U is not contained here. So anyhow, maybe it's not so easy to follow the details, but the idea is very clear that you have this intersection, and this is a very strong condition, because this means that your preceding entry locus is contained in the linear section of our entry locus. And you expect that if you have enough freedom, then the dimension drops. And here it doesn't drop. And so when we vary, we get a contradiction. So we get a strictly increasing function. And now this means that we can bound the bound this invariance delta from below. Because these are increasing functions, and we know where the first point when it's not zero. So corollary, for all I starting with L2 and till n, this function is strictly increasing. So we can draw, this gives some bound, so we should draw a line here, like this, and we know that our function is somewhere here. What else can we say about this function delta? Next comes the following theorem. We can bound it from above. I recall that C is codimension. And so what is this function? We should draw it here maybe to understand. So we have codimension, we have this, and here we have this. And so our deltas are can be found somewhere in this stripe, if you wish. Why is this? This is very easy, because we have that delta k, we have these inequalities. If k is larger than L2. And of course delta k equal to 0 if k is at most L2 of y. This we know because of the preceding theorem, and this by definition of L2. And so from this it immediately follows that because well, this means that delta L2 plus 1 is at least 1, and so on, and we get these inequalities. And so it's clear that our function grows, and so we can be sure that it satisfies these inequalities. And from this we immediately get the following corollary. From this theorem we get the following corollary. L2 satisfies this inequality, because otherwise this second line would be below, and we'll get a contradiction. So and second, this is first point. Second point, if for some k we have this equality here, for some k, then this equality holds for all larger minus C in this interval. And third point is that if L2 is equal to A, then the smallest possible value, to see the smallest possible value of the codimension, then K2 is equal to N, which means the smallest possible value. We saw that this is the smallest possible value for K2. All these are immediate corollaries of this, because as soon as you get here, you should stay in this stripe, and as soon as you get to the upper bound, you cannot move below. And so that's all for today. And next time, which will be tomorrow, I'll start explaining you what is the relationship of this invariance, in particular the varieties for which they assume extremal values, and the number of quadratic equations. Apparently there is no link, but you will see that there is. So to sum up, we saw today that these invariants for quadratic embeddings have some special properties, namely that this invariant K2, which corresponds to the order, it cannot be low, it's at least equal to the dimension of the ambient space. Second, that the invariants, the deficiencies for quadratic embeddings, they are strictly monotonous, starting with a certain number when they become non-zero, and up to the number n, the dimension of the ambient space. And that they are situated in this stripe, and these are two parallel lines, which one starts at the codimension and the other at this mysterious number L2, and then we'll see what happens with them, and what information can we read out from this invariance for varieties, particular varieties of small codimension. So that's all for today.